This paper presents the design and an initial evaluation of a VR-based architectural design discussion system. In this system, participants, including teachers and students, can discuss and modify or create the object in real time, sharing their ideas with voice and sketching, and roll back to previous state of discussion to make some changes or to start a new direction of discussion. An initial user study shows that the feedback for participants were positive and suggested that the system could be effective and useful for supporting architectural design discussion. In traditional architectural education, design discussion is an important course. In a traditional design discussion course, the designer presents the design solution with 2D drawings and a physical mockup, and then the teacher coordinates the discussion, review, and feedback. The discussion proceeds by using voice and sketching on paper or whiteboard. There are some issues of traditional design discussion. First, all the participants should meet in the same place and at the same time. Second, with 2D drawings and physical mockup as discussion medium, participants cannot visualize and navigate from inside, and a lot of additional mental effort is usually required to imagine what the model looks like from the inside. Also, participants have to pay more mental effort in associating the object represented by 2D sketching on papers with the 3D scene. Last but not least, the physical mockup cannot be modified during discussion, and it is difficult or challenging to roll back to a previous state of discussion to make some changes or to start a new direction. In this paper, we proposed a VR architectural design discussion system aimed to resolve the aforementioned issues in the traditional design discussion. First, with virtual reality, participants can join in the same virtual environment even they physically stay in different places. During discussion, participants can navigate the architectural model at human scale from the inside out, and manipulate the models during discussion, express their ideas via sketching in 3D space or on object surface, and roll back to previous visited place or previous state of discussion. The system also provides several support tools for discussion to enhance the feeling of presence in virtual reality. Here's a small video clip of our system to illustrate the design discussion scenarios. 3 students and 1 teacher are discussing how to modify a platform of the model, and the platform is manipulated during the discussion. This clip is built from the teacher. We use Unity to build the platform of our system. The first Open Unity client will treat as host, and all other clients will connect to host server. When a user modifies models by adjusting the parameters, the host is responsible for transmitting the modified data to Rhino Common through the socket. Then, Rhino Common updates the value to ICP, and Grasshopper regenerates the mesh data and directly transmit it back to the host, also via a socket. The host will again synchronize the result to other client. When a user modifies the model without adjusting the parameters, this operation will transmit to server and synchronize in both server and client. Let's talk about the functionalities provided in our system. First, we provide a personal space widget to do rotation, translation, and scaling, and to create new primitive objects in virtual environment. Second, mid-air and on-surface sketching are provided for participants to express their design ideas. Some other tools such as Minimap, Get-All, and Bookmark also proposed to support the discussion. Finally, an intuitive rollback mechanism is used to guide the user back to a previous state of discussion. Object manipulation using recasting or virtual hand are intuitive and natural, but are still under some constraint. For example, recasting can support only radial movement for translation. Moreover, this method also generally suffers from a lack of precision. Hence, we propose a hybrid method that combines recasting for object selection and object manipulation through widget, aimed to provide more accurate operations and allow more complete transformations. First, we select object using recasting. Then we choose type of transformation shown on the main menu. A widget will appear in front of a user, and user can select axis for the transformation. After axis selection, user drags a bit, which a small cube placed in the center of the widget to perform object manipulation. While doing the transformation on the widget, the amount of translation distance, rotation angle, or scale factor also shows in the widget, and the select object in a workspace is transformed accordingly. To further facilitate this discussion, in addition to create of new object, we also provide mid-air sketching and on-surface sketching. With mid-air sketching, we can sketch a rough wireframe for a rather complex object to express the design idea intuitively. On-surface sketching is used to draw on object surface, such as walls or grounds. Here's a demo video of Immersive sketching. The teacher draws a wireframe representing an object in room space and tells the student where the pose should be added. In traditional design discussion scenarios, participants are usually positioned in a nearby area. In virtual environment, it's quite often that the participants may stay far away from each other. Moreover, navigating in virtual environment in full scope can create a sense of immersion, but may lead to loss of spatial awareness of the architectural model. To reduce the problems, we provide a minimap, which is a top view of a building floor augmented with information about participants, such as their street names, the roles, the positions, and orientations. Minimap could help to enhance the spatial awareness of the virtual building and the understanding of the presence of others. Minimap can also provide an easy way to do teleportation. Participants can directly teleport to any place in the virtual environment by touching a position on the minimap. In this system, we also provide a get-all functionality. As just mentioned, in virtual environment, it's quite often that the participants may stay far away from each other. When teachers like to explain ideas, he or she may expect to have students gather around. Once get-all function is executed, students are automatically teleported to a location close to a teacher and then adjust according to their head direction, such that the teacher stays in front of them. In traditional classroom or seminar scenarios, participants usually take notes about important content or information. However, note-taking in virtual environments cannot be easily supported. Instead, we provide a bookmark functionality to mark a time point for specific state of architectural modeling, corresponding to an important design modification or dialogue. When a bookmark is issued, we store the state of the architectural model as well as the position and orientation of the participant who issued this comment. The bookmark information will be used as a guidance for the rollback functionality, or for the course reviewing that uses the playback of the achieved design discussion content. During the discussion, participants usually have certain level of memory about what happened in the past. When a participant wants to roll back, we guide him or her to find a region of interest by offering a 2D minimap augmented with information about where the actions and bookmarks were made. On the minimap, actions such as object modification or creation are marked by flags, and bookmarks made by participants are marked with yellow stars. In addition to flags and stars, a dashed line representing the participant's path is also shown on the minimap, which reminds the participant which region he or she went through and implicitly put the actions and bookmarks in the time sequence. Since participants usually have clear memory about where the action happened and when they happened, to support rollback to a specific time point, we first revert to a specific region and then select an object that was modified or created in the region to confirm the desired time point. The objects that were modified or created are rendered and highlighted at the positions after modification with color coding for the order in time. Here shows the demo video of rollback. First, user editing the statue, translate and scale it. Then he moved to other place, trying to build an if and pose. After a long editing of ifs, he may want to back to the time point that the pose had not even been added. So he opened the rollback mechanism, clicking a flag to back to a specific region, and choose the top of the statue. Different position of both shows the different brightness, and after he selects one of them, the environment back to previous time, and the pose of the ifs had not been added. Now the user can move to different direction of design discussion. It is difficult or challenging to conduct a user study that compares our system against with a traditional architectural design discussion. Instead, we conduct an initial evaluation to evaluate the system with architectural major students who have already received traditional architectural design discussion experience in real classroom. Therefore, based on their experience, the architectural teachers and students were capable to evaluating the usability and user experience and effectiveness of our system against their prior experience of the traditional architectural design education. Our initial user study question was, to what extent is our system usable, useful, and effective to use in remote architectural design discussion? We divide the participants into 4 groups. In each group, one designer brings his model to a course, and the teacher starts to discuss about the building. He may first navigate the building, editing, and brainstorming to help students understand how to improve his work. There were 5 questionnaires to assessing the user experience, impression, and effectiveness of our system, including simulator sickness, presence and co-presence, cognitive and physical workload, system usability, and system evaluation questionnaire. In applied and research constructs with complex VR applications, it has now become standard practice to measure this constraint that we have totally measured in our system. We believe that it sheds light on different aspects of the user experience and were highly relevant to the simulation experience of VR architecture design discussion. Fortunately, all the participants did not give up after a few questions and stay focused in the post-experience questionnaires around 30 minutes. In the simulator thickness questionnaires, the difference in score, which indicates thickness caused by experiencing design discussion in virtual reality, was not significant. In presence and co-presence questionnaire, users usually have feelings or being present in the virtual design discussion during their experiment. About the question 12, the virtual world seems more realistic than the real world, has a lower grade. It is reasonable since the model in virtual environment is a plain model without realistic texture and lighting. NASA TLS questionnaire measures the effort in the system. The result shows that mental demand, physical demand, and effort has relatively high score. The high mental demand score shows participants were engaged in a discussion. The high physical demand may be due to the hardware problems, such as head-mounted display. The high effort means the user feels that he spent more energy to achieve their level of performance. With linear regression, we observe that for a unit time period, the effort required for object transformation is much greater than for sketching. Most of the scores in IBM System Usability Score questionnaire get high. The extremely low score happened in question 6. It was easy to learn to use this system, which means only 20 minutes is not enough for user to learn how to use the system. More time for training may be necessary. In question 9 and 18, some users think we do not provide enough error messages, and some functionality seems to be expected but not available, for example, copy and paste. Our comprehensive system evaluation questionnaire that we designed consisted of two parts of evaluating our system's functionality, which is overall system evaluation and system interactive functionality. In overall system evaluation, all the questionnaires get high score, which means users usually agree that our system is interactive, enjoyable, and useful. While considering each functionalities, we found that all functionalities get high score, and translation performs better score than rotation and scrolling. We guess that's because we only provide object information in both personal and object space. This may imply that providing object modification in both object and personal space is a better model to facilitate growth to find changes. Most of the participants like the present VR architectural design discussion system. They think the system is easy to use and provide an effective way to share their designs. More than half of the participants' comment on min-map functionality were positive. One participant said, "I can quickly know the structure of the building. It also helps the user to locate others during discussion." Some participants are suggesting that we should allow users to adjust the scale of the 2D min-map because they want to see more details of the building. Most of the participants like the interface of object manipulation present in our system. One participant said, "I can move objects precisely with translation in personal space. It's convenient to me." Many participants like the sketching functionality. The sketching is also helpful to facilitate the architectural design discussion. Since the rollback functionality can be applied by the instructor only, we have feedback from 2 instructors who used the rollback interface during the discussion. Their responses are positive. In the meanwhile, some participants point out several drawbacks and limitations of the present system. Some drawback comes from hardware limitations, such as head-mounted display. Some participants mentioned that they could not tell if they touched the interface or not. Additionally, the process of object manipulating can be improved, such as snapping. And others want to add some more functionalities, such as object copy and paste. As a concluding remark, we present the design, implementation, and initial evaluation of a VR architectural design discussion system. The expected goals were that the participants can have not only much better spatial understanding about the architectural model, but also more effective and efficient design discussion experience. The result of our initial user study indicate that the aforementioned goals have been reasonably achieved, and that some functionality provided in the system are helpful for architectural design discussion and learning.